Okay, so today we're going to cover topics in number theory and kind of supplement the combinatorics or the counting side that we learned. Okay, if you guys hear me saying combinatorics, I'm referring to counting. That's also another name for it. Okay, so let's look into number theory. So first off, prime factorization, that's one of the most important things. By definition, number theory is the study of integers and their properties. And just a refresher, what integers are numbers that go from, like start from, negative infinity, and they go on -5, -4, -3, -2, -1, 0, 1, 2, 3. So like that. The prime factorization of n is an expression for n, which is a product of the product of powers of prime numbers. And so the fundamental theorem of arithmetic basically is a really common, well-known theorem, but all it is saying is that in its essence, it's saying that every positive integer n has a unique prime factorization. So there's only one way to write it out as a prime factorization. And like I said, what a prime factorization is a product of powers of prime numbers. And this is all in words right now, so you might not understand what I'm saying, but as I start going through and we start writing a little more, you'll understand what I'm trying to say. The form of a prime factorization is this way. Now this makes more sense. So it says product of powers of prime numbers. So P1, P2, P3 are all prime numbers. And E1, E2, E3, all the way to EK and PK are all exponents. So that's how it's written. And so P1 to the power E1 is obviously, so it's like taking P1 to the E1 power, so that's the power of a prime number, and then it's the product of all sorts of things like that. So note that P1, P2, P3, and so on till PK are different when written in a prime factorization. And so I guess I'll write this down. Because as it says, there's only one unique prime factorization, and if P1 was equal to P2 for some reason, then there's multiple ways you can write it down. So in essence, that's what a prime factorization is. And as we start to do examples, we'll start to understand what it means. Prime factorizations can be very useful. It is an important skill to have to be able to prime factorize a number, and especially when it comes to simplifying fractions or determining factors of a number. If you recall, we had the n choose r and NPR formula, and in those cases, prime factorizing a certain number can come useful to cancel out the numerator and denominator, for example. So that's just one example of using prime factorizations. There are many other ways to do so. And it ties in also with divisibility, which we're covering next. So divisibility is really connected with prime factorization, and given a positive integer n, you can normally use divisibility rules to kind of break n down into prime factorization, because you need to figure out what P1, P2, P3, all the basically prime factors are. And to do that, you can use divisibility rules and say, okay, if it matches if a number n passes the divisibility rule, then one of its prime factors is a set number. On the other hand, given a prime factorization, you can also find the factors of a number n. And we'll kind of look into this sort of idea when we do examples and short exercises. So without further ado, let's get into our divisibility rules. So first of all, our divisibility rule for 2, that is the most common one that many of you know. a number has to be even. When put in English, you say a number has to be even, then it's divisible by 2. And when I say divisible by 2, what I mean is when you divide by 2, divide n by 2, your remainder is 0. And so that's what I mean when I say divisible by 2. So divisible by, so if n is divisible by k, that's the way you write it. K divides n, so this bar means divides. K divides n if and only if n over k has like a remainder 0. So now that for divisibility rule of 2, it's easy. The last digit has to be even. If you think about it, the number has to be even, but in essence, the last digit has to be unit digit has to be even. But for powers of 2, you can actually generalize this rule, and that's what makes it really handy and useful. So a number is divisible by 2 to the power n if and only if the last n digits of a number are divisible by 2 to the power n. And what I mean is that let's say we have a number 1,736,542,8. So I want to know whether this number is divisible by 4, for example. So I just take the last 2 digits, 2 and 8, and take the number that it forms. So the number it forms is 28. And I check if 28 is divisible by 4, and it is, right? Because 7 remainder is 0. So that means this whole huge number is divisible by 4, which is a really powerful method to figure out things. You could also see that the number might be divisible by 8 or not. And what you would do for that is take the last 3 digits, right? So 428 is the number formed by that. You check if it's divisible by 8. It actually is not. So this number is not divisible by 8. And obviously, if it's not divisible by 8, it's not going to be divisible by 16, and so on and so forth. So you can just stop there. So this can also help in determining what the largest power of 2 that goes into this number is, and things like that. And again, this ties into figuring out either solving word problems or trying to figure out prime factorizations. Okay, so moving on to the next divisibility rule. So these are some of the stronger divisibility rules. This is one of the widely very used and strong one, which is the divisibility rule for 3 and 9. So a number is divisible by 3 or 9 if and only if the sum of its digits is divisible by 3 or 9, respectively. And what that means is if a number has, digits that sum to, I'm going to say K, or let's say C. If 3 divides C, then we get that, so I'm going to call a number n, then 3 divides n. And if 9 divides C, then 9 divides n. So that's a way of putting it. So if a number n has digits that sum to C, then 3 divided by C, 3 divides C implies that 3 divides n, and 9 divides C implies 9 divides n. So that's basic divisibility for 3 and 9. One important note is that unlike powers of 2, this does not work for higher powers of 3, like 27, for example. It only works for 3 and 9. And if you guys are interested, then I would also recommend you guys to look at the proof. I really found this one of the neatest proofs I've seen, so you can search it up. The divisibility rule, proof of divisibility rule of 3 and 9. But just remember that unlike the powers of 2 rule, that higher powers of 3, right, like 3 to the power 3, 3 to the power 4, etc., would like not work. Okay, now we're coming to some familiar ground, which is divisibility rule for 5 or powers of 5. So a number is divisible by 5 to the power n if and only if its last n digits are divisible by that power of 5. So this is very, very similar to our divisibility rule for 2. It's basically a parallel. And so you can just use whatever rules. So for example, if we had 3, 1, 2, 5, we know this is divisible by 1, 2, 5 because the last 3 digits are divisible by 5 to the power 3. So things like that. Divisibility rule for 7. This is, I would say, by far the more involved one. So we're going to come back to this one at the end. Let's skip over and go to divisibility rule of 10. Divisibility rule of 10 is really straightforward. If a number is a power of 10, then the exponent, whatever the largest power of 10 that divides a certain number n can be determined by the number of zeros at the end of the number. So if there's 6 zeros at the end of this number, right, then the largest largest power of 10 that divides this number is 10 to the power 6. Divisibility rule of 11. So I would say some of the harder ones are divisibility rule of 11 and 7. 11 is not that hard to remember. So let's go through that one first, and then we'll go through 7. So first of all, let's see. I'm going to take an example after I read what the statement is. And it says a number is divisible by 11 if and only if the alternating sum of the digits is divisible by 11. So now that sounds like really complicated English, but we're going to try to put that into an example, and I'll try to show you what I mean by that. So let's pick a number, and I'm going to pick something I know that's divisible by 11. So I'm going to pick 1331, and then I will exemplify that it's divisible by 11. So what they're saying is the alternating sum of digits is divisible by 11. So alternating sum of digits. So I'm going to go, let's start numbering. So I'm going to go A, B, A, B. So you number from, so the process is you start numbering from right to left and, lettering from right to left. So you go A, B, so on and so forth. So now you write out all the A number, like digits. So 1 and 3. And then you write out, so these are the A, and then B you write out as 1 and 3. So that's 0. And 0 is divisible by 11. 0 is divisible by any number, so you could just go with that. So 0 is divisible by 11. So hence we have that 1331 is divisible by 11. So the alternating sum part is a little confusing because you might think that you should sum the two of them, but you actually take the difference between the two groups, and this should be B. So it could also be such that, let's take another example. 1090, or let's see. 10912. Yeah, that should work. Okay, so what that means is, so now you number it. So 10912. Oops. So it's A, B, A, B, A. So I'm just going 1 plus 9 plus 2 minus 0 plus 1. And that's equal to 11. So that's 11. And 11 is divisible by 11, right? So that means this complicated number that I just randomly wrote, 10912, is divisible by 11. And so you see how powerful this is, because you can easily try to solve problems or try to find out what the divisibility of a number is. A huge number, 5-digit, 6-digit, even larger, because these rules are proven for any number of digits. And so that's really useful to have. So I would focus on trying to remember this one. And again, this one, which we'll go over right now. So truncate the last digit of n, double that digit, and subtract it from the rest of the number. If n is divisible by 7, if and only if the result is divisible by 7. So let's take a number like 343. And so what we're going to do is we take the last digit out. So truncate means cut it off. So when you cut it off, you get 34 and then you get 3. So you double digits this digit, and you get 6. They're saying that you subtract that from the rest of the numbers. So you have the remaining number is 34. So you go 34 minus 6, and then you get, that's 28. And 28 is divisible by, 28 is equal to 7 times 4. That is divisible by 7. So 343 is divisible by 7. So that's a way of testing it. So the process is you cut off the last digit, you multiply the cutoff digit by 2, and you take the remaining number and leave it there. Then you subtract that product, like the doubled version, from the leftover number. And then if that is divisible by 7, then your number is divisible by 7. If you, for some reason, end up with a huge number, then you just keep going until you reach a point that you can see whether a number is divisible by 7 or not directly. So if you had like a 5-digit number, then if you truncate the last digit and then subtract, you're going to end up with a 4-digit. It's sometimes hard to recognize whether a 4-digit number is divisible by 7. So you could do the same process with that 4-digit number and keep going until you see whether the number is divisible by 7 or not. So 7 is the harder one to do. Sometimes it's just easier to divide by 7, like do the long division, divide by 7, and see if there's a remainder or not. So I would just try to we'll just try it for the sake of trying it, but I personally stick with dividing by 7 for 7 most of the time because it's just quicker to do so. Okay, so here's some prime factorization quick exercises. So I'm going to leave these up here, and then in the next video, we'll so you guys take some time to try to factorize these using the divisibility rules, and the formatting of prime factorization, which, to remind you, is P1, E1, P2, E2, and so on and so forth till PK, EK. And remember that P1 not equal to P2, not equal to P3, and not equal to PK. So just remember that. Take some time and try to prime factorize these. Remember, according to fundamental theorem or arithmetic, there's one unique way of trying to prime factorize every number. So we'll all end up with the same answer if we're correct. So just take your time, do the problems, and we'll come back and discuss.